In this video, we're going to take a look at the squeeze theorem and how we can use it to prove and work with a very important limit, one of these 0 over 0 indeterminate forms. The basic idea behind the squeeze theorem is that if you have a function, in this case f, you're trying to find the limit of f at this particular c value, and we don't have any methods that we can use like in the previous lessons, one option is if you can find a function that's always greater than it, like g of x, except at that point. And if you could find another function h that at least in the neighborhood is always less than f of x. And if it turns out that the limit of h of x and the limit of g of x happen to agree to some value L, well, if g and h both agree with their limit and f is trapped between them, then f of x's limit must also equal L. So we call this the squeeze theorem. Sometimes it's referred to as the sandwich theorem because the limit of f of x is squeezed between functions g and h. One of the important consequences of the squeeze theorem is that it can be used to prove these three special limits. The one that we're going to focus on in this video here is the limit as x approaches 0 of sine of x over x equals 1. We did explore this a little bit earlier numerically, right? If you think about the limit sine of x over x, right, as x is approaching 0, the denominator is heading to 0, the numerator is heading to 0, but no simplifying is going to work. We can't factor, use conjugates, common denominators. There's no trig identities that help us. The squeeze theorem eventually is what's used to prove this limit. The other two limits are important as well, and they have some applications, but we're going to just kind of limit the scope of things that we're focused on here and take a look at just this particular limit. There are some pretty well provided proofs out there. The basic premise behind the proof is if you take a look at this unit circle here and we take a look at the inner triangle, the pi wedge arc, and the upper triangle, those three areas, right, are going to be set up here that can then be used for the squeeze theorem. So it'll be able to be proven that this somehow and this somehow traps this area in between it, and then the limit with some algebraic work can determine that the limit of sine x over x as x goes to 0 is 1. I'm not going to go through the proof here. Maybe I'll do that in another video, but there's plenty of existing proofs of this theorem out there, so we're just going to move to the next issue of how to use it. So we know, and I'll just put it here so it's in front of us, it's something new, the limit sine of x over x as x approaches 0 is 1. We have this limit. The question is, how do we use that to solve a limit that's slightly different than that? A couple things we want to kind of point out that what's important is not the x, but if we had the limit as u approach 0 of sine of u over u, we would still expect that limit to be 1. And in essence, basically, anytime the angle and the value are both heading to 0, we would expect the limit to be 1 as long as the angle, x here, and the denominator agree. Okay? So before we try to solve this one and come up with a technique, I just want to explore a little bit here. If we had sine of x over x, we already know that one. If I made the numerator the same as the denominator, we'd be already in business. We'd know how to use our limit. But if I had the limit of sine of 7x over 7x, right, I would also be able to use this limit. I could use a quick, simple substitution, let u be 7x, right? This becomes u, this becomes u, and u is still heading to 0 because if x is going to 0, 7x is going to 0, right? So the point is that as long as the denominator and angle agree and they're both heading to 0, we know that the limit would in fact be 1. Okay? So if we go back to the original problem, we have two things we could think about doing. We could either try to get this 7 out of here, right, out of the angle to make the denominator and angle agree, or we could try to put a 7 down here in the denominator to make the angle and the denominator agree. As tempting as it may be to pull the 7 out, we know that that's not possible. As a quick explanation, the sine of 7x, right, is going to be between -1 and 1. If we pull the 7 outside, right, now you're bouncing between 7 and -7, and it's just not a valid algebraic or trigonometric property. So it's tempting, but you can't do it. And in general, it's going to be very hard to change this angle. We would have to start thinking about addition angle formulas or double angle formulas, and all of those get complicated very quickly. However, it's not that hard to get a 7 down here. Right? In fact, when I'm solving a problem like this, I'll just start with a clean question here. Like other things we've done in math before, I like to think about what I want it to be. I would like it to turn into sine of 7x over x. And rather than just visualizing it, I like to have it down on paper. This I know I can handle. Okay. So the question is, what do I have to do to the original expression I was given to make it sine of x over 7x, give or take a few things. But I know that I can multiply by 1. And if I decide to multiply by 7 over 7, right, I can simply move this 7 over here. Right? And the only difference is I'm left with the 7 over 1. Okay? Now, this 7 over 1, right, is just a constant. We had a property that said it can come outside the limit. So we're going to get 7 times the limit of sine of 7x over 7x, which is going to 1. And this answer is just 7. Okay? So if we can make the angle and denominator agree by multiplying by some specific representation of 1, right, then everything left over is just a constant. That constant can be factored outside the limit, and the limit of that sine of the angle over the angle as the angle goes to 0 will be 1, and we can use this property. We'll look at a few more examples, and sometimes we have to make sure, as we have more things going on, we have to make sure we understand what the issue is, right? What I didn't really take time to do in that last one was explore the 0 over 0 scenario, because we had just done one like it, but I'll do that here. If I try to let x be 0, the numerator is 0. The cosine of 0 is 1, but this x here is going to make the denominator 0. So we really don't have much choice. We don't have any other options at this point other than limit as x approaches 0, sine x over x is 1. Okay. So if you notice, the part that's causing the problem is over here, right? This is something that we can make equivalent to this, give or take some constant multiple. This cosine of 2x isn't really a problem, right? When x goes to 0, the cosine of 0 is going to 1. So we don't have to really worry about that cosine of 2x. It's not going to cause any problems. So when I'm working out a problem like this, again, I want to think about what I'd like to see. I can't change the 3 angle, right? The angle multiplier of 3 here. I can change the 4 though. So I really want to have a sine of 3x over 3x. Right? I already have the x, but I don't have the 3. So I'm going to multiply by 3 over 3, right? But I look ahead, see what I want, and then figure out what to do to get there. Okay. But I can't just throw away all the extra stuff. I just want to kind of organize it and regroup it. Okay. So this 3 comes over here. The 4 is going to come over here. So I'm going to have a 3 here. I have a 4, and I have a cosine of 2x. And it's a good idea at this point to kind of look around and make sure you didn't miss anything. Everything we have on this line is equivalent to what we had on the previous line. The important thing is that since the angle and the denominator agree and they're both going to 0, this whole thing is going to 1. Right? When x goes to 0, cosine of 2 times 0 is going to 1. So this really becomes 3 times 4 over 1, or 3/4. Okay? So focus on what the problem is. It's that sine x over x, or the sine of 3x over 4x. Move things around, manipulate them, reorganize them so that you can use the limit property that you have at your disposal, and then see what you can do. I wanted to look at just a couple quick examples. And after you've been doing these for a while, it might be tempting to just say, well, this limit is 1, but that's not in fact the case, right? Because when you take limits, it's not just the sine x over x that's the issue. It's the value, right, that x is approaching that matters. So I got a little lucky on that first one where I didn't really think about it. But when x is approaching pi, the sine of pi is going to 0, right? But the denominator is actually just going to pi. Sine x over x is perfectly well defined as long as x isn't going to 0, right? So in this case, the limit is not in fact 1, it's 0, okay? It's important that while there are certain things that will draw your attention, like the sine x over x, you have to take the whole limit into account, including what the value x is approaching. Okay? Now in the second example, right, the tangent is 0, 0, 4 times 0 is 0. So we do have a 0 over 0 case. And even though tangent wasn't in our rule, we might still be thinking about using the sine x over x rule as x goes to 0, because tangent of x is really sine x over cosine of x. So I can rewrite this as sine x over 4x times cosine of x. And now this pretty much looks like the example we just did, right? The cosine is not really causing the problem. The 4 is not really necessary. We can separate those out. And in this case, right, since there's nothing being done to the x and the angle here, right, we can just leave an x behind. We don't need to put anything in the denominator to get it to match the angle. Once again, this limit is going to 1 because x is going to 0. This is going to 1 because x is going to 0. And in this case, we just get a quarter. Okay? So if you know what you need to use, and you can sort of think what it's going to take to get there, then this becomes a pretty routine process.